Using the blast transforms. I threw away my chalk. I'm so excited for that. I just love it. See you soon.
What the fuck are you?
Good morning, fellow mathematicians. Welcome back to another video. I wanted to upload something else originally, but I thought I might spice up your weekend a bit. It's going to be bloody amazing today. We are going to fuck shit up really badly. We are going to tackle this bad boy right here. This is going to be the best thing you will see this weekend. Bear with me, it's going to be quite a long video, but it's going to be worth it. Absolutely amazing. That's the best thing I ever came up with when doing integration. I don't know, I just found this out and I wanted to share it with you guys. Links to all the corresponding videos will be in the description. There are going to be a lot of videos in the description today. This bad boy right here, what could we do with it? Maybe we could introduce a parameterization at first. Let's call a new integral I in terms of t. And we are going to define it as follows. That's the integral from 0 to infinity of sine squared t times x over x squared plus 1 dx. And by now you guys should know why I'm introducing a new parameter inside of an integral. We want to differentiate this integral right here, and we are going to do it. So we are going to use the Leibniz rule for integration on this one. So when we differentiate I in terms of t, we are getting I prime in terms of t. But what exactly is that? Well, if we differentiate this integral, the upper and lower bounds aren't dependent of t. That means we can use the special case of the Leibniz rule for integration, and we can just interchange this differential in front and this integral sign. We are interchanging them, and we are getting a partial derivative in terms of t inside of this integral. So we can conclude we are getting the integral from 0 to infinity of the partial derivative in terms of t of sine squared t times x over x squared plus 1 dx. 1 over the denominator is independent of t, so we can bring it in front of the differential and we just have to differentiate sine squared tx. What is that exactly? That's the integral from 0 to infinity of, okay, so we are getting 2 times x times the sine of tx times the cosine of tx over x squared plus 1 dx. Great thing, you might notice, doesn't that we cancel out? So this simplifies quite a bit. And here in the numerator, that's 2 times sine times cosine. Well, that's the double angle formula for the sine, so we can conclude something else. This simplifies it a lot. So that's now the integral from 0 to infinity of the sine of 2 times t times x over x times x squared plus 1 dx. Whew. So that's the first thing we found out. And now, no, I'm not going to do the thing you might think I'm going to do. I'm not going to integrate this right here. That's not the point of the video. That's going to be the amazing thing of this video. We are going to differentiate it again. Now, we are ending up with I double prime in terms of t. What is that? Well, upper and lower bounds are independent of t. That means we can interchange integral and differential and turn it into the partial derivative of this integrand. So we have the integral from 0 to infinity of the partial derivative in terms of t of sine 2 times t times x over x times x squared plus 1 dx. 1 over the denominator is independent of t, so we can bring it in front of the differential and we can just differentiate this numerator right here. So that's now the integral from 0 to infinity of, what are we getting? We are getting 2 times x times the cosine 2tx over x times x squared plus 1 dx. Great thing. Doesn't that we cancel out? And we are at the next stage, my boys. And I'm not going to do the thing you might think I'm going to do. I'm not going to integrate this right here. We are going to differentiate it once again. It's getting exciting. We are doing something we've never done before. So let's differentiate I double prime in terms of t once again. So we are getting I triple prime in terms of t, third derivative. Once again, the upper and lower bounds are independent of t. Interchanging integral sign and differential, turning it into the partial derivative. So this is now the integral from 0 to infinity of, we have the partial derivative in terms of t, of 2 times the cosine 2t times x over x squared plus 1 dx. This 2 is just a constant, so we can bring it to the front of the integral. And also 1 over the denominator is independent of t, so we can bring it to the front and we just have to differentiate this cosine term. So we are having 2 times the integral from 0 to infinity of, okay, this is getting minus 2 times x times the sine 2t times x over x squared plus 1 dx. That doesn't look any good right now. It just seems like we are making things worse. So at first we could bring this minus 2 to the front to make a minus 4 out of that. Okay, that does look a little bit better at least. But the thing is, we are having this x times sine of x here and this weird x squared plus 1 term in the numerator. So what could we do? Maybe we could do some algebraic manipulation. That might be a great idea. Maybe we could expand this fraction right here, this integrand, by x over x. That's just 1, that won't change anything. So we are getting x squared right here and x times this chunk in the denominator. Okay, and here's a multiplication sign in between. So it wouldn't hurt us if we would add a 0 to this x squared. That won't change anything, so that's a great idea. So we can add a 1 and subtract a 1 right again. So we are having this in the numerator right now, x squared minus 1 plus 1 times sine of 2t times x. How is this any good? Well, I tell you how this is any good. Let's just distribute a bit and let's see what we get. So right now, this is minus 4 times the integral from 0 to infinity of, okay, at first we are getting x squared plus 1 times the sine of 2tx, and then minus the sine of 2t times x, and this whole thing over x times x squared plus 1 dx. And we just made this numerator additive, so we can break up this fraction and we can use the linearity of the integral to make this into 2 integrals. Don't forget to distribute your minus 4 into everything. So right now we get minus 4 times the integral from 0 to infinity of, okay, so this is x squared plus 1 times the sine of 2t times x over x times x squared plus 1, okay, dx, that's the first one, and then minus, and minus 1 becomes positive, so positive 4 times the integral from 0 to infinity of sine 2t times x over x times x squared plus 1 dx. And by God, my boys, this is looking absolutely amazing, because this and that we cancel out, and this thing is just following me around all day long. This right here is the Dirichlet integral, and we know what it will evaluate to. I already calculated it 3 times, and we have the up and lower bound from 0 to infinity. That means this integral right here will evaluate to pi over 2. That's amazing. And what is that integral right here? What the fuck are those? I'll tell you what that is. If you take a closer look, this is just that bad boy right here, I prime in terms of t. Oh, what a coincidence. So this is I prime in terms of t. So what we end up with is just I triple prime in terms of t. It's nothing else then. Let's distribute this minus 4 into here, so we get minus 2 times pi. So that's great. And also we get positive 4 times I prime in terms of t. Wait a minute. Wait a minute. What is that right here? I'll tell you what it is. That's a differential equation. And we can give those integrals a slightly new name. For example, this right here, I primes in terms of t, is just j in terms of t. Okay, so j for Jens, the mathematical mean guy. And that would mean that I triple prime of t is nothing else than j double prime of t. So this right here is j double prime in terms of t. So this right here is also j double prime in terms of t equals to minus 2 pi and then positive 4 j in terms of t. And this right here is just a second order, ordinary, linear, differential, inhomogeneous equation. What a long term, and we are going to solve it now using Laplace transforms. I threw away my chalk, I'm so excited for that, I just love it. See you soon. Like I said before, we are going to use Laplace transforms on this one. I haven't derived anything regarding differential equations till now except for Laplace transforms. So we are going to use this as our desired tool for today. So what I want to do is I want to apply Laplace transform to this differential equation. We are going to use our already derived identities, and what we end up with is s squared, f in terms of s, and then negative s times j of 0 minus j prime of 0. So this is this term, and this is equal to, so what do we get? This is minus 2 times pi, but the whole thing over s. So that's the identity, and then positive 4 times f in terms of s. And now we want to bring f of s to one side and all the other chunk to the other side, and then we want to use the inverse Laplace transform on everything. So we have to do some algebra. So what do we end up with? That's equivalent to saying we have f of s, and this times s squared. We are bringing this to the other side, minus 4, okay, and on this side we are adding this to both sides, so we are getting s times j of 0, and then minus j prime of 0, positive j prime of 0, I'm sorry, and then negative 2 times pi over s. Great thing, but I said we want to isolate f of s, so we have to divide both sides by s squared minus 4 under the condition that this isn't equal to 0. So let's do this, let's divide everything by that. So this is s squared minus 4, this is also s squared minus 4, this and that we cancel out, and we end up with our desired expression for f of s. And now we are going to apply the inverse Laplace transform to both sides. So that means the inverse Laplace transform of f in terms of s will give us j in terms of t, which is our solution to the differential equation. And this is now just the inverse Laplace transform of this whole chunk right here. So at first we are getting s j of 0 over s squared minus 4. So this is the first part, and we can use the linearity of the inverse Laplace transform to break everything up. That's quite a lot of work. And then positive, the inverse Laplace transform of j prime of 0 over s squared minus 4, and the last part, the last part is just positive the inverse Laplace transform of, so we have this in the numerator, so this is 2 pi over s times s squared minus 4, and then we would be done. But we have to do a bit more work. So you might notice j of 0 is just a constant when it comes to the Laplace transform, the inverse Laplace transform. So we can bring it to the front at first. So this is j in terms of 0. We can bring it to the front. Same thing with j prime in terms of 0. So this is positive j prime in terms of 0. This is now 1 over this. And also, I forgot a minus sign right here. We could bring minus 2 pi to the front. Let's do this later on. I don't have enough space right now. This right here is quite easy. We can identify this term right here as the hyperbolic cosine cos of 2 times t. That's the inverse Laplace transform of this right here. But what is that? I might give you, why is it even the cos of 2t? Well, we can write 4 as 2 squared. And this will be our argument right here times t. Same thing here. We are having 2 squared right here. But the thing is, this is going to be the hyperbolic sign. But something is missing up here. We would need a 2 up here. How can we get a 2 up here? Well, up here there was just a 1, so we can rewrite this 1 as 2 over 2, so we have to bring over 2 to the outside. So that thing will evaluate to the hyperbolic sign of 2 times t. And here's the worst part, we are having this. And this denominator doesn't look any good. We have s times s squared minus 4, so we have to do some partial fraction decomposition. We have to do it. We can't find any way around it. unless we use, for example, the convolution theorem. I haven't derived this till now, so we are going to do it the traditional way. Do we have any information that we can use on this one? Well, the good thing is, when doing partial fraction decomposition, we just need to have the ability to read. So how can we break this up? Since we have two factors down here in the denominator, we want to break this up into two new fractions in total, into the sum of two new fractions. So at first we are getting a over s, the degree of this denominator is 1, so we need a degree of 0 up here, and then positive b times s minus c, for example. And then over s squared minus 4. This is having degree 1, so we need degree 2 right here. And this is a positive sign, it doesn't quite matter. And now we want to multiply both sides by this big denominator under the condition that it isn't equal to 0. So what we end up with is just 1 is now equal to s, and s will cancel out, so we end up with a times s squared minus 4 times a. That's nice. And then s squared minus 4, and this will cancel out, so we end up with positive bs squared plus c times s. Okay, great thing. Can we conclude anything? This polynomial has a degree of 0 on this side, but this polynomial has a degree of 2 right now. So we need to get rid of everything that's higher than degree 0 on this side. So that means as squared plus bs squared need to be 0. That's the first condition. So as squared plus bs squared need to be 0, but that also means that a equals to minus b. Okay, that's the first conclusion. So we got rid of those two terms. Next thing, well, this thing has degree of 1, but we don't have anything else with a degree of 1, so that means that c is equal to 0. That's the next conclusion. C is equal to 0 in this case. And what we end up with now is just that 1 is equal to minus 4 times a, but that also means 4 isn't equal to 0, minus 4 isn't equal to 0. We end up with minus 1 over 4 equals to a. But we know what b is just minus a. So that also means that b is equal to 1 over 4. So that concludes our partial fraction decomposition, and let's see, I'm just writing it here. We are having the inverse Laplace transform of minus 2 pi over s times s squared minus 4. Okay. What is that now? We get minus 2 pi, we can bring it to the front, and times the inverse Laplace transform of. Okay, so the first part is minus 1 over 4 times 1 over s. So this is just our partial fraction decomposition for this term right here. And then positive 1 over 4, and don't forget that we have an s up here, so we need to drag this s with us, and this is s over s squared minus 4. Okay, great thing. So we were able to conclude this, and now we can use the linearity of the inverse Laplace transform to break this up. This is now minus 2 pi times the inverse Laplace transform of, okay, minus and minus becomes positive in total, so this is just a positive sign, and we have 1 over 4 times 1 over s. This will just be 1 over 4. So the inverse Laplace transform of 1 over s is just 1. Okay, and then negative 2 pi times the inverse Laplace transform of 1/4 s over s squared minus, and I'm going to rewrite this 4 as 2 squared. Okay, great. So this right here will just be 1 over 4 times the hyperbolic cosine of 2 times t. I'm going to conclude everything on the next chalkboard. We've come a long way. And this right here is now the solution to our differential equation. Everything we've concluded till now. Okay, great. And don't forget, that was j in terms of t, and that was j prime in terms of t. But a Laplace transform always gives us an initial value problem. So we have j in terms of 0, so when t is equal to 0, and also j prime when t is equal to 0. Okay, so let's at first plug in 0 into this equation right here. Well, this is going to be the sine of 0, and this will just make everything vanish. We are getting a 0 integrand. So this right here is equal to 0, and especially that means this whole term is going to vanish. That's fine. Okay, if we plug 0 into here, well, our cosine will just be 1. So we can conclude that j prime in terms of 0 is nothing else than 2 times the integral from 0 to infinity of dx over x squared plus 1. But we can actually solve that. That is just 2 times the inverse tangent from 0 to infinity. So this is 2 times the inverse tangent of x from 0 to infinity. Well, the inverse tangent of 0 is just 0, and our tangent would go to infinity if x, if this would just be pi over 2. So the inverse tangent of x when x goes to infinity will be pi over 2. Sorry, I mixed that up. So 2 times pi over 2 will just give us pi in the end. So that's a great result, I guess. So this will just be pi over 2 times the hyperbolic sign. Now we can use the definitions in terms of the exponential function of the hyperbolic sign and the hyperbolic cosine. Let's write it out a bit. So we get, this is pi over 2 times. So this right here is something over 2, so we can bring this 2 to the outside. So this makes pi over 4. Great. And we have e to the 2t minus e to the minus 2t. Okay, nice. And then minus pi over. This will also give us something over 2, so we can bring this 2 to the front. So this is pi over 4 times e to the 2t minus, plus e to the minus 2t and positive pi over 2. But the great thing is, well, this term and this term will cancel out because we have a minus sign right here. So this will vanish. And what we end up with is just minus pi over 4 e to the minus t, 2t, and the same term. So we have this term 2 times. 2 and 4 will cancel out, so we have pi over 2 times e to the minus 2t positive pi over 2. That's amazing, we've solved the differential equation. But do you know what is even better? If we would just integrate j in terms of t, we would kind of get to our original integral that we wanted to find out. So remember, j in terms of t is nothing else than I prime in terms of t. But what was our initial condition? We know that our original integral I is nothing else than I when t is equal to 1. Let's see what our original integrals were. I totally forgot to write them here once again. So this was our original I, and this is I in terms of t. And now you will see where this came from. So if we let t equal to 1, this would just give us our original integral. But is there a condition that would make, for example, I in terms of t vanish? Well, if we plug in 0 into this t, this is sine squared of 0, so this would just give us 0. So I in terms of 0 would make everything vanish. So that's something we can conclude. So what we want to do? We want to integrate I prime of t from 0 to 1. That's our point here. So this now means the integral from 0 to 1 of I prime in terms of t dt. Well, what is that? This is I at the point t equals to 1 minus I at the point t equals to 0. But we just concluded this is going to be 0, and this right here is just going to be our original I. That's what we want. Okay, so let's integrate the solution to our differential equation right here. Don't go away, chalkboard. Okay, so this is the integral from 0 to 1 of, we get pi over 2. And we have minus pi over 2. Oh my goodness, I totally forgot that. We have a minus sign right here. I'm terribly sorry. So we have minus pi over 2 times e to the minus 2t, and then positive pi over 2 dt. And this is so easy to integrate. We get now minus and minus will become positive. So this is pi over 4 times e to the minus 2t, and then positive pi over 2 times t from 0 to 1. If we plug in 1 into here, well, that would mean at first that we get pi over 4 times e to the minus 2 plus pi over 2. If we plug in 0 into here, so that's the second part of our integration, well, that would just be 0 right here, but e to the 0th power is just a 1, so we get minus pi over 4. But pi over 2 minus pi over 4, well, that just gives us pi over 4. So in the end, our final answer to our integral is pi over 4 times e to the 2. I'm bringing this in the denominator, and then positive pi over 4. And that's the solution, my boys. Oh boy, what a ride! I came up with this yesterday. Completely randomly, I just stumbled upon it. It just blew my mind, and I wanted to share it with you guys. And I hope you guys enjoyed this video. I hope I made your weekend a bit more joyful. And well, if you like this video, please like and subscribe, and recommend me if you like. Share this video on Facebook, show it to your friends, to your mother, to your grandma, to your newborn son, I don't know. Get him to like mathematics. And if you want to support me a bit more, I would highly appreciate it if you want to support me on Patreon. I'm doing all this stuff for free. If you want to support me, I would appreciate it very much. And up until the next video, have a flammable day. See ya!